Are we only coding today? Oh, no. I got slides, too. I heard from a TA, one of the students told them that whenever I go to IntelliJ in lecture, they turn off the stream or the video, whatever they're watching it on. Like, is that really how some of you all study? If I'm not doing slides, you don't even pay attention? You don't even watch? That's crazy. But I do have some examples in the slides. We'll go through a few recursion examples, and whoop whoop, the stack is coming back. But at the end, if I do get through all the slides, I do want to go to IntelliJ and run the debugger on these examples so we can get another visualization of how they work. Yeah, Tetris. We were playing some Tetris together online. Somebody pasted the link in chat for a Tetris game, and I'm like, you know what? Whatever. It was like half an hour after lecture already. I was still just chatting with them. Yeah, today's lecture question, factoring part 2. Jay Narrow, hey, you can still hang out with us, you know. You don't have to miss it. Sly Cooper. That is one thing I wonder, like when the view count is already horribly low compared to enrollment, and then I wonder how many of those are not even students in the class anymore. Or never were. Like my view count might be inflated a bit compared to I was just kind of sitting here for a few seconds, if that's what you're wondering. You're seeing the loading circle? Yeah, I'm trying to start the stream earlier. I'd like to start early and, you know, at least chat with you and maybe even go through examples before lecture, but, you know, things happen. Today on Fridays, I have a 199 recitation that ends 20 minutes before, and there's usually students with questions, and I'm finishing up there. But as soon as I was done with that, I switched right over to this. But whenever that holds me up, I can't do it. And then Monday, Wednesday, I have no excuse. It, you know, just happens. Top stream for basic programming. Oh yeah, hype. Jay Narrow got the notification. Yeah, I wonder if that happens too. If you're just watching streamers and then lecture starts, you're like, oh, I guess I'll watch my old professor. Henry Cavill, I don't know who that is. Yeah, I'll give you a preview. I mean, well, I'll talk about it in 2 minutes, but it's exactly the same lecture question as before when we did factoring the first time, but no var. So you have to write it as a recursive method this time. That's the twist. But it's the same exact thing. So like the testing, you already have your test cases from the other time we had this lecture question. You can use the same exact test cases, so I don't need to test your testing again, so Autolab is only going to test completion. So use those same tests and then rewrite that method in a different package, the functions package, not the whatever package it was, lecture I think last time. So in a different package, but write the same functionality as a recursive method. And if you haven't done the first one yet, there's no excuse. Once you finish this one, this also works for the one without var being banned. So submit the same thing to the other one, and you'll have credit for both of them. So once you finish this one, you better have credit for the last one. For those of you who are on top of the course and on top of your game, yes, there are a significant number of students who still have not finished the first factoring question, and it is very concerning to me. The class in general is very far behind. Since I mentioned it, I'll pull up the number. Test factoring. I'll give you a few stats. For those of you feeling like you're behind, I'll give you a few stats. And you probably are behind if you're feeling that way. But credit, so 229 enrolled. We've had quite a few resigns already, so we don't quite have that many. But 229 started the course. 129 have credit for the first factoring question. Only 164 even made a submission to the factoring question. 1, 2 question 1, 2. For Monday's lecture question, if you really are feeling like you're behind, this should give you an idea where you stand with the class. Wednesday's lecture question, which I recommend everyone finish by Wednesday night to make sure you have that stuff. Only 39 of you have credit. That's how just horribly behind the entire class is. And I don't even know what to do about that. I think it's because of being online only. I think that's at least part of it. And then part of it is just having a very loose interpretation, my very loose interpretation of what a deadline means. I think too many students are using that as an excuse to slack off. But I don't know what to do about it at this point. Yeah, seriously, Mango Mutiny. I'm with you. I can't even understand. And, I get that it's harder to stay motivated when it's online only, but this bad across the whole class, there's no excuse for that. Like, I know it's a hard course, but when you still haven't even submitted lecture question 1, 2, we're on 3, 3 right now. You haven't even submitted? Come on, man. Work with me here. It's a hard class. There's only so much I can do to make it more palatable. You got to meet me. But I don't want to dwell on this because, let's face it, those students aren't here. What's up, Grudge? Those students aren't watching live lectures. They're letting the videos pile up and then binge watch them. They're probably not hearing this until, the second to last week of class. When it's way too late. Yo, Andrew Paul. I just realized that you're in my 199 recitation. Not to call you out or anything or leak info. But yeah, what's up? Just saw your website. Yeah, and then the homework. Oh my goodness. I think a lot of students just give up on the homework and focus on the learning objectives just so they can pass. But let's have the class need some ass whooping. And then that's where I get conflicted. Like, is that really my job? My job's to teach you computer science. I know that. But does it really include staying on top of you to make sure you do what you're supposed to do? I just... Like, I'm not a babysitter, though I feel like it most of the time. Make sure you do your homework. I can't just have a suggested deadline and have people follow that. No, I have to enforce it. I don't want to go back to enforcing deadlines. I really don't like the stress that causes. But I might have to. If this is the way things are going to be, I'm going to have to go back to enforcing deadlines on lecture questions and saying, do it by midnight or that's a 0. But that doesn't really fit into my 5 or fail grading structure, so I don't know. I might just say let them fail. But a lot of them will come crawling to me at the last week of classes and the TAs. Oh, I can't, the line is too long for office hours. I can't even get any help right now. Well, yeah, because you passed up your opportunity for 13 friggin' weeks to get help. But anyway, I'm just going to rant if I talk about that. And y'all don't need to hear that. Because I'd imagine none of you are those students that I'm talking about anyway. It's preaching to the choir, as they say. So let's get into some recursion. So the lecture question, as I just mentioned, but let's get it in lecture proper, is a flashback to the factoring question. So factoring, finding the prime factorization of an input number, except this time put it in a package named function. So don't just edit your current method and then submit that. It does have to be in a different package. So in a functions package, create a algebra object method factor that takes an int and returns its prime factorization. Same exact rules as last time. I just cut and paste this and change the word lecture to functions. Same exact question. The difference here is that var is banned. Just like we started on Wednesday, the var keyword is banned. So the intent here is to write this as a recursive solution. So write some recursive method to be able to factor the input and return that list. And my hint for this is you can use return statements. We usually don't use return statements in Scala. It's it tends to be considered bad practice for the Scala community specifically. But this time it's something that really makes this a lot more feasible, a lot more doable if you put a return statement inside of a loop. So if you're looping over potential factors and you find one that is a factor of the input, you can hit a return statement right there and then return that level of the recursion and end that stack frame with a return statement. It is a bit bad practice. There are ways to avoid that and have cleaner, better code, but we really haven't talked about that yet, so I can't expect you to do it. So for this one, let's just slap a return statement inside your loop, and you can write this method. You already wrote the test for this when you did lecture question 1-2, so I don't need to test your test again. You already have valid tests for this. You already know how to sort the output, sort the lists of integers and stuff like that. So I'm not testing your tests again. I'm only testing your functionality, testing the completeness against my tests. So I'm not testing those again, but you should use the tests that you've already written to help your debugging process as you're working on this question. So take those tests that you've already written for the other factoring question and use them here. And once you finish this, if you are one of those people who haven't finished the lecture question 1-2, once you finish this also works for lecture question 1-2, assuming you wrote your tests. Submit to that and get your credit for both of those. Or if you're still working on 1-2, work on both of these questions together. Once you get it, you got it done for both of those. Oh yeah, and remove var if you have var in your previous test. Good one, UB macros. Marcos. Why does Scala community not like return? That's a good question. I don't have an answer off the top of my head for you. I think it's to do with messing up the control flow of a program. When you have a return statement anywhere in your code, it's a lot harder to tell when that method is going to end. You don't know when it's going to end. If you don't have a return statement, you know it's going to end when you hit the closing brace. So I think that's why, but don't quote me on that. There could be a deeper, more involved reason. If you use recursion for 1-2, as long as you didn't use the keyword var, yeah, go for it. Submit the same code again. Yeah, breakable loops. You can do breakable loops. That's not something I teach, though. I do see it in a lot of student submissions. You get on Google and find Stack Overflow, and it tells you how to do a breakable loop in Scala. I'm not going to stop you from doing that, but it's not something I'm going to teach either, to do breakable loops in Scala. And Scala doesn't have a break or continue, doesn't have those keywords. The language just isn't built for that. But there is a breakable. You wrap your loop in a breakable, and then you can break from it. But it's just not something I'm going to talk about. But if you want to use it, I'm not going to stop you. All right, so let's talk about recursion. Let's see 2 examples today. And these are examples that I teased earlier in the semester. I showed you these as recursive examples. And when I talked about them, I mentioned that, hey, don't worry if you don't really understand the recursion right now. We're going to talk about them later. It's later. So let's talk about it. So this example, compute geometric sum, computes the sum of the values from n down to 1, then returns that sum. So this compute geometric sum of 3 should sum 3 plus 2 plus 1 and return 6. So that's the behavior we want. You deleted your... Grudge, come on. You deleted your algebra from the beginning of the semester. Just go to Autolab and you can download your submission. All your code is backed up on Autolab. So just go there, download it, and then you can get any of your old code. You're geniuses. Oh, I thank you. So we wrote this as a recursive function. So now, or a method in this case. So let's break down the pieces that we saw last time. We saw the base case when I did my kind of formula of how to write recursive functions, because that's what we want to talk about now. Having a base case, which has some trivial input-output behavior, writing your recursive part, writing your method, logic of your method, with the assumption that the method is already correct, and then making sure that you're always getting closer to your base case in any recursive calls that you make. Those are the 3 ingredients to having a successful recursive method or function, to be able to have some good recursion in your life. That's how we're writing our recursive functions. What's the storage limit on Autolab? Probably the size of the hard drive. I don't know off the top of my head. Don't use it to back up your code. That's why we have limits on submissions. The submission size is capped at 2 megabytes per file. So don't use it as your cloud storage. Just don't do that. unless you break your movies into 2 megabyte chunks, wouldn't be worth it. Anyway, all right, so the base case for this is some trivial input-output behavior. I have some trivial input I know the output for. I can usually hard code it in most cases. That's going to be the base case, or base cases. In some, for some problems, we'll have multiple base cases. So we have a base case for this one, geometric sum. I'm going to say 0 is my base case. That's a trivial input-output. I'm going to say if the input is 0, you return 0. And I'm also going to put a less than or equal here to handle any negative numbers. I'm going to assume that the problem statement that I'm solving says on any negative or invalid input, just return 0. So I'm going to say if n is less than or equal to 0, I'm just going to return 0. Trivial input-output. I don't have to think. I don't have to compute anything. I just say input 0, return 0. Done. No big deal. So our base case should, in most cases, until you get to really complex recursive algorithms that you're designing, for most cases, your base case is going to be very trivial, very simple, easy to compute. In this case, just nothing. Just return 0. Nothing to do there. If you're not in a base case, you're going to hit the recursive step. So the recursive step is going to make a recursive call somewhere in it. So somewhere in the recursive step, you're going to call the method that is already being called. So we call compute geometric sum of 3, and compute geometric sum of 3 is going to call compute geometric sum of 2. So we're calling the same exact method that we're writing. And this is where it can feel like magic, but it's just technology. It's just computer science. We're talking about science, not magic here. So the recursive step we're going to write, assuming that the method is already correct. So we're going to assume that compute geometric sum does return the geometric sum of its input. We're going to assume that that's true. And we're going to write our recursive step based on that assumption. So if compute geometric sum is already correct, I can get away with something like this. I can say compute geometric sum of n minus 1. While I'm computing the geometric sum of n, compute the geometric sum of n minus 1. Recursively, I'm going to assume that that returns the geometric sum of n minus 1. And if I have the geometric sum of n minus 1 already, I can add n to it. And that's going to be the geometric sum of n. The geometric sum of n is equal to n plus the geometric sum of n minus 1. So with a little math, I know that this is, if compute geometric sum is returning the correct value, which I'm assuming it does, then this is going to return the correct value for n by calling it with n minus 1. And Mundane Madman, the short answer is the stack and the frames. Hey, there we go. RT Keenan hitting it. Getting it, man. And we'll show the example. We're going to show the stack in a second with this example. And very importantly, the third step, the third ingredient to our successful recursion. The first was the base case. The second was assume that we're already correct and use that assumption to build our logic. The third one is making sure any recursive call we make gets us closer to the base case. We always have to get closer to the base case with each recursive call, or else we're going to go infinite. We're going to get a stack overflow. Everything's going to break. So when I call compute geometric sum, I can call this with anything that makes sense. I could call this with compute geometric sum of n minus 2, and then add n and n minus 1, and then I might have to add a new base case. Actually, I wouldn't have to in this case, the way I wrote it. So we have to make sure we're getting closer to the base case. We can write it in different ways as long as the recursive call is getting us closer to the base case in all inputs. So no matter what n is, if I call compute geometric sum of n minus 1, that's always going to take me one closer to the base case of n less than or equal to 0. And this is where the less than or equal to gets us out of some trouble. If we just had if n equals 0, return 0, and somebody decides to call this with negative 1, well, now we're no longer getting closer to the base case in our n minus 1. If negative 1 takes us to negative 2, takes us to negative 3, we're never going to hit our base case. I shouldn't say never. Actually, probably never. We wouldn't hit our base case until we underflow an int, go back to the max value of an int, the highest positive value, and then go all the way back down to 0. We would eventually hit that base case, but before that happens, we would overflow the stack. So we would never actually get there. We'd have the stack overflow before we underflowed our ints. If you understand that sentence, you are doing fantastic, by the way. And so we're always getting closer to our base case. Our logic is flawless, and our base case is trivial. Those are our 3 ingredients for successful recursion, and that's what makes this recursive method work. An underflow, so an int overflow is when you go over the maximum value for an integer and it wraps around to the greatest magnitude negative number. An underflow is just the opposite. You go too far negative, you get to the largest negative value and then subtract 1, and you underflow all the way up to the maximum value. So it goes both ways. You can either go too high and wrap around to the big negative numbers, or too low and wrap around to the big positive numbers. So eventually you'll underflow and wrap around and then get down to 0 again. But not a stack underflow, an int overflow. A stack underflow wouldn't really make sense. I guess that's just when your program ends and the stack's empty. Yeah, it kind of does. So ints are represented in 32 bits. You have 1 bit for the sign and then 31 bits for the value. So the highest number you can represent is 2 to the 31 minus 1, or negative 2 to the 31, I believe, or 2 to the 31 plus 1. I might be off by 1 there. So once you go past either of those numbers, it wraps around to the other one. Because once you add that next bit and it's all ones, you add that next bit, it's overwriting the sign bit, and then your sign bit flips, and then you get the behavior that you don't want. All right, so let's take a look at this on the stack, and I'm going to jump right to where we're about to hit the base case. Earlier in the semester, when we first talked about stack, we went through this step by step, and I showed you exactly how we get to this point on the stack. We should be past that, so I'm going to skip a lot of that and just quickly walk you through how we got to this point. So we have the main method. That's where our methods always start. That puts a frame on the stack. And the one piece of information I'm going to add now is each time we put a new frame on the stack, I'm going to explicitly annotate where we left off in the other frame. So the main frame, when it gets to line 11, it gets to this compute geometric sum specifically, compute geometric sum of 3. This method call puts a new frame on the stack. It creates the frame. It creates a variable for the input parameter, assigns it the value of the input argument, and the main frame is going to remember where it left off. So the main frame is waiting for compute geometric sum of 3 to resolve so it can continue its computation. So this frame is just happily sitting here waiting for this frame to return its value so it can assign that value to result and go on with its computation. When we get to compute geometric sum of 3, put that parameter on the stack. N is not less than or equal to 0, so we hit the else. And we get to this line, compute geometric sum of 2, since n is 3 in this frame. So we're going to put a new frame on the stack. The parameter equals 2 this time. And we're going to remember, I'm waiting at line 5, waiting for this stack frame to return. Once this stack frame returns, we're going to give control back to this stack frame at line 5, and it's going to continue its computation. Whatever this stack frame returns, that's what this method call resolves to. We're going to add that to n and then return that back to the main frame. This stack frame does the same thing, gets to line 5, compute geometric sum of 1, put that on the stack in a new frame, just idle on line 5, just wait on line 5 for this stack frame to return, and this is where we are at this point. Are those pointers are that is confusing, isn't it? I guess I didn't really use the term pointer though. I used the term reference, so maybe it's not too confusing. But these are different than what goes on the heap. These are program pointers. The program the JVM in our case is waiting on that line. So this frame is going to remember where the program was executing. It was executing on this line, this statement right here. So it remembers when it gains back control of the program, when control goes back to that frame, it remembers where to go. We call that a program pointer. I believe, actually, I'm a little iffy on that, if it's called a program pointer or not. I think that's how I learned it, is calling it a program pointer. So the greater the value, the more space this program... Oh, yeah. So, like, if I call compute geometric sum of 100, this program is going to take up more space on the stack. It won't actually take up more space because there is a certain amount of stack space that is reserved. Whenever you start a program, the JVM is going to say, here's your stack space. And that space is reserved for your program, but sometimes you just don't use up all that space. Sometimes you use very little. If I say compute geometric sum of 100, I'm going to use up more of the stack space that has already been allocated for that program. So there will be more read and writes to RAM and more usage of that stack space. But it's not like you won't see the RAM usage go up. Like if you monitored your program and watched the RAM usage, it won't go up because it's only using already allocated memory, which is the stack. When you start abusing the heap and start using a lot of heap space, then you can actually run your programs. If you write a really inefficient program that creates a lot of very large lists and puts them on the heap, you can actually watch that in your OS, whatever your OS is, to monitor your RAM usage. You can actually see your program. It should be called Java, and you can use your program, watch your program eat up all your RAM. But this won't because it's the stack. So, download more RAM. What's my favorite Pokemon? Maybe after lecture. I don't know if I really have one though. So we get to this part of the recursion. Oh, I got off track there. I know there was something else I was saying there too. But we get to this part of the recursion, and now we're about to hit our base case. Oh yeah, that's what I was going to say. So we can say 100, and that'll take up more of the already allocated stack space. And there is a point where we'll go too far. It's going to be different based on your settings and your operating system and your JVM and all that. But there will be a point where you're going to go too far and you're going to use up all of your stack space and get the stack overflow. If we do compute geometric sum of 1,000,000, we're going to overflow the stack the way this is written. So here, let's advance this. We're calling compute geometric sum of 0. We're going to put that frame on the stack. The input is 0. And we're going to execute one line at a time. So now we're picking up, actually following how the JVM is going to run this code. We start at line 1, the first line of the compute geometric sum method. We evaluated this. We put n as an int on the stack, assigned it the value 0, the input argument. And we hit the open brace and start executing this code. We hit the conditional. The condition is true this time. So we hit our base case of 0 and just return 0. Nothing else to compute. This is the last line of the method. We hit a close brace, which just leads to another close brace. Nothing else to do. So this stack frame is going to return. And notice at this point, this is the deepest level of the recursion for this call. We have all these frames on the stack just sitting around waiting for the return values to start coming back up the stack to get all these values back, so each frame can continue its computation and return its value that it's computing. So now we start to go back up and hit these idle frames, return the values, and have it return back up the recursion. So here we're returning 0. This stack frame is going to be destroyed and give its value back to this stack frame that was sitting on line 5. It was sitting on line 5 waiting for this call to return. That call is going to return with a value of 0. So now we get that value of 0 from the other stack frame, from this method call that we've made. And now we can continue. We can finish the computation. So this returns 0. We're going to add n to it. N, we look for that inside this stack frame. So notice that we have multiple values of n on the stack, which is kind of where we get our simulation of variables from. We have a value of n. If we did this with a loop, we would have one variable named n, and we would keep reassigning its value. When we use recursion, we put multiple values of n on the stack that never change their value, but since we have multiple values of n, we can kind of simulate the same behavior without using a variable. This can be a val. This n is immutable, meaning it cannot change its value at all. But we didn't use a variable. But we kind of simulate a variable without using a variable. So now we're going to add n. It's 1 inside this stack frame. We don't look outside of the stack frame. So we don't see this 2, we don't see this 3. We're going to see the 1, add 0 and 1. We all know that's 1. And then that's the last line. We hit a close brace, we hit a close brace. No other statements to execute. No other expressions to evaluate. So this is the last expression, so that's the return value of this method. And we're going to return 1. This stack frame is destroyed. We return 1 back to the previous stack frame, which was waiting on line 5 for this stack frame to return. We get that value of 1. We add n to it in this stack frame. N is 2. And we return 3. We go back up the recursion. Oh, let me back up one. This returns 3, and we go back up the recursion. This frame gets their return value of 3, adds it to its value of n, which is 3, and then returns that, returns 6, and we just keep rolling up the recursion. We keep returning from those stack frames. So we put a bunch of frames on the stack for each level of this recursion, and then we hit the base case. That's what stopped us from going infinite, and then we start returning back up the stack and up all these stack frames so they can start being destroyed and start getting back to our original method. So now this method's going to return 6 back to the main frame. So if we're just calling this and not caring about all the recursion or how this is implemented, we just see we call this and it returned 6. From the main method's perspective, that's all that happened. This method, we put a stack on the frame and it returned 6. This method actually put a bunch of more frames on the stack and did a lot of extra computation, not extra computation, but it put a lot more frames on the stack and then returned all those frames through the recursion. But we don't have to care about that in the main method. All that's gone, all that memory is freed up, all that stuff is popped off the stack, and now we get our return value of 6. We print it to the screen. We continue on our program, print to the screen, and program over. Recursion is like throwing a ball up in the air and then getting a completely different ball back. Yeah, recursion's tricky. If it shouldn't make complete sense yet, but if it's starting to make sense, go through more examples like this. We'll do one more today. Not with the stack and the slides. I'll go to the debugger for that part. But go through more examples like this. Run the debugger yourself and watch all those frames go on the stack. And you'll start getting the idea of what recursion is doing. Obviously, this is a simpler example, so let's go to a tougher one. But I'll pause for a second and let all this sink in a little bit. Time to enjoy the stream. When you explain the stack for the learning objective, you don't have to talk about the pointer. I'm talking about the pointer here to emphasize how the recursion is working, to try to make that a bit more clear. If you don't mention the exact line numbers, like in the quizzes, I don't think we even print the line numbers in the things. But as long as your explanation implicitly shows that you do understand that execution is picking up where it left off after the return value, that'll be fine. You don't have to. We're not specific on formatting for those questions, as long as you understand the concept of that, of picking up where you left off when a stack frame returns. I just found out I used recursion for the last lecture question. Oh yeah, you're supposed to. Used recursion and didn't even know it. Awesome. Okay, no more questions. Let's talk about anagrams. So hopefully everyone was able to follow that example pretty well. We've seen that example way earlier in the semester as well, but now we're talking about the recursion side of it and how that part of it works, with the goal of being able to write recursive methods at this point. Anagrams, yeah, I'm not going through this in 5 minutes this time. I was running out of time when I showed this the first time. When I did anagrams. But I did use var last time we saw anagrams. And I am going to give one of the similar warnings from the first time we saw anagrams, that the code isn't quite going to make sense, and that's fine. There are a lot of things I'm going to use here that are not going to be explained until the next functional programming lecture. So I'll briefly explain them in this lecture, but if those ones don't make sense, that's fine. Just suffice to know that that this will do the same thing that we saw last time. Namely, I think it's my next slide. I'll explain it real quick. So in this, and then maybe quickly now and then again when we get there. But this is going to iterate through the input, all the characters of the input, remove each character one at a time, make a recursive call on the remaining characters, that string with that character removed. And then the recursive call is going to return, then we're going to append to everything returned that character that we removed. And just to back up a little further, anagrams, given an input string, return a list containing all of the possible rearrangements of the characters of that string, is what we're trying to compute here. Just a reminder what an anagram is. So let's take a look at this, and I want to focus on how to write a recursive method. I want to go through those 3 steps in our formula again, but with a bit more complex example this time. Because that's one of the complaints I always get. Oh, your examples in lecture, they're so trivial, and then what you ask us to do is way more difficult, which is a valid complaint. So here's a trickier one. Let's talk about it. You don't need to be able to read all this code yet. There is... I'm using a lot of things. Yield, flatten, distinct, map, this underscore syntax I very briefly mentioned. Those things shouldn't make sense to you right now. I will talk about each of those very briefly in the last slides of this lecture. But we'll get there. Yeah, the underscore is a wildcard, but it's used in a little bit different context in this code. But in general, yeah, it's a wildcard. Okay, so let's talk about this. Let's go through our steps. We need a trivial base case, write our algorithm with the assumption that our algorithm works, and then make sure we're always getting closer to the base case in each recursive call. Those are our 3 ingredients to successful recursion. So let's see if we applied them here. Base case, input. If the input length is 1, if I have a string with 1 character, I'm going to return a list with just that string. So if the input for completeness, I probably should have another base case for length equals 0 and return an empty list. I should have that here just to make sure I don't have that edge case where it can break. But if the input is length 1, I have a string of 1 character. Say I just give it the character A in a string. All anagrams of that character, of that string, are just A. I can't rearrange a single letter any other way. So just like when we did merge sort and we had a list of size 1, well, it's already sorted. There's nothing left to do, nothing we can do here. So this is a trivial input-output behavior. That's a great base case. Length is 1, return a list containing just that string of length 1. Done. Base case done. Base case should always be that easy. Just find a trivial input-output behavior. And if you design ahead, you can start mixing these 3 steps together. Design ahead and pick a base case that you know you can always get closer to in your recursive calls. But we have our base case. And worth noting, this is the only time in this algorithm that a new list is created. And this is fairly common. There's a lot of what do I want to say? A lot of recursive methods where this is the case, where the base case is the only time where you're actually creating anything, and then in the recursive step you're just adding to that. We did the same thing in geometric sum. The base case is the only place where we actually started a number, and then as we came up the recursion, as we returned from those stacks, return those frames on the stack, that's when we were actually doing our computation. So we dug all the way to our base case, and then as we came back up, that's where we're doing the math. So we're doing the same thing with anagrams. We're creating a list, a trivial list here, and as we come back up the recursion, after we put a bunch of frames on the stack, as they start returning, that's when we're building up bigger and bigger lists with all the rest of the anagrams. So our recursive step, we're going to write the logic here. Oh, I was wondering, what are you doing? Oh, you heard the dog got up from his nap. The recursive step, we're going to write this with the assumption that our algorithm is correct. So we're going to write, as we're writing the anagrams method, we're going to call the anagrams method with the assumption that the anagrams method is already correct. This is can seem like the counterintuitive step, but we're just going to assume that anagrams is correct. So sparing the details of yield, map, flattened, distinct, underscore, sparing those details, what we're doing here is iterating over all of the indices of this string. For each indice, so for each character of this string, we're going to remove that character and create a new string that's identical to the input string, but with the character at index I removed. We're doing that with the substring method. Give me the substring from index 0 to I, exclusive of I. And then give me the substring from index I plus 1, inclusive of the first one, and exclusive of input.length. So it's and then concatenate those two strings together. So we have a new string that's just the character at index I removed. So give me that string. Recursively call anagrams on it. So give me all the anagrams of that string, that new string, which is the same as the input, but with what character I removed for each index I. And then for each value that's returned, for everything in that list that's returned, all the anagrams of that string with the character returned, append that character to it, is what this map is doing. So append that character to it, to each of those elements in that list. So if anagrams is correct, then this code should also be correct. If I get all the anagrams of all of the substrings, all of the strings that I created from this input by removing one character at a time, get all of those anagrams, and then append the removed character to each of those returned anagrams, then I should have all of the anagrams of the input. Yeah, yield is in Python too. Y'all are asking the same questions over and over though. I gotta keep moving through lecture. So if anagrams is correct, then my logic follows that my overall algorithm is going to be correct. And without using var, of course. So the code got a little harder to read because I'm not using var here, by using a bunch of functional programming ideas. So the recursive step here, the important thing, the last ingredient of this, is that my recursive calls always have to get closer to the base case. So luckily a string can't have negative length. So for completeness, I should have a check for length of 0 here, which I don't have. So for completeness, I should have that. But assuming that we don't have an input of size 0, we're going to get some input length that's greater than 1, so a string with at least 2 characters in it, if we're hitting the recursive step. When we hit the recursive step, we're removing a character and then making a recursive call. We're always making recursive calls on the input string, but with one of its characters removed. So if I remove one of the characters, I've successfully decreased the length by 1. And assuming the input string is not length 0, I am getting closer to a length of 1. So I'm always getting closer to my base case with each recursive call. And that's our 3 ingredients for successful recursion. We have a trivial base case, We have sound logic, assuming that our algorithm works, our method already works. And each recursive call gets us closer to the base case. So if we never did reach the base case, if we didn't remove a character, maybe we added a character, just left the string the same, or whatever, we're never getting to the base case, and we're going to overflow our stack. Yeah, not using var is the same thing as immutability. And we'll talk about immutability. Immutability, we'll give it a name. We'll talk about that when we pick up functional programming. The last 2 lectures of functional programming. How many alphabet do we have? I don't even know what that means. How often do you not incredibly often, but fairly often. There are certain problems where recursion is easier. I know it always seems, when you first learn especially, it seems like it's a lot harder than just writing loops, but there are certain situations where using recursion significantly reduces your workload. So whenever I come across one of those problems, I use recursion. And specifically when we get to trees in this class, trees will be our first example of something that's much easier to do with recursion, to work with recursion, tree traversal specifically. Much easier to work with recursion. And when we get there, I even have a slide on it. I'll remind you when we get there. But I'll show you how to do tree traversals with recursive methods. And then I'll have a slide and I'll challenge you to do the same things without recursion. And I promise you it will be significantly more difficult than writing them with recursion. So if we have an input, I guess it will. If I have an input at, we're going to go through this loop. We're going to remove a from it, make a recursive call with just t, which returns t. And then append the a back to it, and then remove t, make the recursive call with just a, returns just a, and then append the t to it. So we get both of those values, and then we could return that if this were part of another step in the recursion. We would return that to some call with input of length 3, give that list to that, and then keep going. Why today's lecture question so late? Did I put the wrong due date? I might have. I'll check it after lecture. All right, so let's talk about very briefly about each one of these things that we see in this example. I mean, even when it says submit late, it doesn't. The deadlines for lecture questions don't really mean anything, except the December 11th at midnight deadline. That one's serious. Don't miss that one. But it's strongly recommended that you follow the deadlines. But hey, most of the class is ignoring me on that one anyway. So I don't know. See you in December. Well, hopefully you pass. I'm pulling for you, but if you're not even trying, there's only so much I can care. So let's go through these one at a time. The yield keyword is it goes as part of a loop right in between the loop, the start of the loop, the for, and then the braces or the parentheses, and right before the opening brace. If you put the keyword yield there, instead of just running the code of the loop for each value in the data structure, it's going to collect the values in the loop. So the loop body, whatever the last, kind of like a method, returning the return value of a method, whatever the last expression to be evaluated in that loop is, for each iteration of the loop, yield is going to say collect all those values into a data structure and return that data structure. So this entire loop, everything in parentheses here, is going to return a data structure containing the values of the last statement, the last expression that's evaluated in the body of the loop for each of these for each of these values in this data structure. So from 0 until the input length, we're running this loop, and each time we get to the last value, the last expression, whatever this resolves to, that's going in a data structure. Since this returns a list, we're going to end up with and then I'm going to convert that list to a list, or this the resolution of this for loop with the yield to a list, because it's not going to be a list, it's going to be a sequence. So I want to make that a list just so I can use a list of lists, because we've seen lists all semester. So I'm going to convert that to a list, and since this is a list, we're going to get a list of lists of strings as our output. Map is going to apply a function to each value in a data structure and return a data structure of the same type with that method applied. So I get all the anagrams of this new string, and I'm going to call map, which is going to give me a new data structure with this function applied. This function is going to append the character that we removed to the end of each value in this data structure that's returned by anagrams of new string. It's right here. So, and this underscore, this is shorthand for creating a function. Last time we created a function using parentheses, a parameter list, the big arrow with the equal and a greater than, and then the body of the method. We can do the same thing here, but you're going to start seeing this code pop up using underscore as a shorthand to reduce the amount of code that we have to write. So this allows us to skip the parameter list and the big arrow and just write the body of the function where the parameters are replaced with underscores. So we don't name the parameters, we don't have a parameter list, and we can do this as long as the type of the parameters can be inferred, and we only use each input parameter once. And then if we have multiple underscores, the order in which the underscores appear in the definition of our function is going to be the same as the order of the parameter list. If none of that makes much sense and you don't want to think about it, just write functions the way that we did when I first introduced first order functions. Write the parameter list and write out the whole thing. This is only shorthand. It's just made to reduce your typing. So if you don't want to think about it, just don't. And then flatten and distinct. These are methods that work on our list. Flatten, I have a list of lists here. Flatten is going to turn that into a single list containing all of the elements from all of the lists contained in that outer list. So I have a list of strings. I'm going to convert that to a single list of strings containing all of the values from all of the lists. And then distinct is going to remove all the duplicates. So this is how I avoided doing the duplication check that we did last time. I'm going to call .distinct, and that's going to remove any of the duplicate values. Oh yeah, gen algorithms posted. I forgot to mention that. I'm sure most of you aren't ready for that. Most of y'all didn't even do the last lecture question. Maybe most of y'all that are here, though, have done it. Okay, so that's... and that brings us back to the lecture question. I didn't bite. It's not something to brag about. So at least quickly... anagrams of, and we don't have much time. I was going to ask for a 4-letter word and see what kind of funny crap I got, but I'm just going to pick one. I'm going to say good. And I want to set a breakpoint. I'm going to set a breakpoint at my base case and then run this in the debugger so we can see the frames on the stack. Yeah, but I hope a lot of the class is going to catch up. It's really getting to that point where things are getting serious here. If we're almost midway through the semester, if you're still slacking off, I mean, there's more work being piled on, I'm sure, for all of your classes. I know it's tough to keep up on an online only, but at some point you got to suck it up and do it. And I don't know, I'm starting to get worried for the class. So let's look at what we have when we call this method. And a lot of it we won't see the internal details because this is happening. This code is so dense that the debugger is only going to go a line at a time and not really show us everything. But what I want to focus on are the frames on the stack. So when we get to our base case for the first time, we get there with an input of D, but I want to focus on how we got there. And you'll notice we have a lot of other frames on the stack. That's because of all the functional programming goodness that we're using in here. Each one of those, like we have an anonymous function that we created, function that we never named. That put a new frame on the stack to call that. So there's a lot of extra stuff. The yield, the map, a lot of extra stuff is going on the stack, but I'm just going to focus on the stack frames for methods that I wrote, excluding the anonymous function because, I don't really care. But the anagrams stack frames. So whenever anagrams was called, and we can see which line we're on as well, by the way. Anagrams, we're on line 8. If I go back to the previous call, the frame on the stack that's waiting for this frame to return, this one is sitting at line 10, waiting for this call to return, which is actually this entire thing. This is all one large statement. So we're waiting for this to resolve, which contains a yield, a map, an anonymous function, a recursive call, a toList call. There's a lot of stuff in there, but really we're waiting for that to resolve so we can assign this to output. So on this recursive call, we have the input OD, and that is being waited on by this recursive call with an input of OOD. And this method is waiting on, it has an input of good, waiting on line 10, waiting for that frame to return. And then we get to our main frame, which is sitting on this line 20, waiting for this anagrams of good to return. So when we go down our stack, we see one character being removed. We got an input of OOD. This loop is going to remove one character at a time, starting with the first one. Remove the O, make the recursive call. Remove the O, make the recursive call. We have a D, we hit the base case, and we can step through our program here. We return a list containing just the value D. And here we see our input is OD. Our new string was D. We removed the O. And now we get to our... I stepped through this before lecture. It's a little tough to see because there's so much happening in one big statement. But we can get to returning. So now our input is OD. We removed O and made the recursive call of D. That returned. So now we're on the next letter. We removed the D. Our new string is now O. We're going to make the recursive call with just O. That hits our base case, return a list containing O. And now we have the return values of both of our recursive calls. So we made multiple recursive calls, one for each character in the input string. Now our return values are going to be the list containing O and the list containing D. For the list containing O, we append D to it. For the list containing D, we append O to it. And we end up with our output containing a list containing two lists, DO and OD. This is all the anagrams of the input OD. We've correctly computed all of the anagrams of that input value just by combining the return values of the base case. Then we're going to flatten and remove duplicates and return the list containing DO and OD. That returns back to the call with OOD. That removed the O, made the recursive call of OD. Now it's going to remove the second O and make another recursive call with just OD. We're just going to make a recursive call with D, make a recursive call with O. And that's going to return the same thing in this case. That's going to return a list of DO and OD. And then we remove the D and do OO. And I want to advance a bit. So I'm going to move my breakpoint and I'm going to click this go button. And that's going to run the program until it hits another breakpoint. So I'm going to set a breakpoint here and just get to where we're collecting values. And I can see on the input OO, I removed O, made a recursive call, appended O, removed O, made a recursive call, appended O. We got OO and OO. So when this returns, we should just get one list with OO. So now I hit go again, advanced again till we hit this breakpoint. And now on the input of OOD, it got its return values from all three recursive calls. One with this O removed, one with this O removed, and one with the D removed. With this O removed, we got with this O removed, we got DO and OD and appended the O to each one of those. With this O removed, we did the same exact thing. Nothing changed. And then with the D removed, all the anagrams of OO was just OO. And then we appended the D to the end of that. So now we have all of the anagrams of OOD. We're going to combine those into a single list and then remove the duplicates. So we're just going to get DOO, ODO, and OOD. So if we advance that, we won't really see it quite right away. Let me get to... And then it just goes, you can see how much work, how many recursive calls are being made. Oh man, I went right past it. I wanted to stop on the top level call of good and then see all the return values. But hopefully you get the idea at that point. So a little over, but let's stop lecture right there.